Hello everyone, I'm Michael Ralph, and today we're going to be talking about correlation. We're also going to be doing regression analysis a little bit later in this process. So let's go ahead and get started. I have set up the skeleton of a spreadsheet already. I'm going to assume that you've seen some of the past videos to try and expedite this process. So I have two data sets. I have set 1 and set 2, and these are matched pairs. And what I want to know is, as the first set increases, so as I move along the first data set, is there any correlation in the movement that I see in the second data set? You can see that it's not a perfect match, but is there any correlation as these numbers increase? Do these numbers do anything related? Do they increase or decrease along with the first data set, or are they completely unrelated? So to do this analysis, I am first going to establish a null hypothesis that says that they are completely unrelated, that they are totally randomly matched, and that there is no correlation. So if that's the case, what should that look like? So we're going to do some resampling here. I want to start with setting up a column of random numbers, and that's exactly what it sounds like. I just want a whole bunch of random numbers. So I'm going to use a random number generator in Excel to make a whole bunch of random numbers. You can see they have nothing to do with anything. They're just totally randomly chosen. And then what I want to do is I want to rank those random numbers. I'm going to do the rank EQ function, and I want to tell it to rank the number right next to it. And I want it to be the rank within this set of numbers, and I'm going to copy and paste this formula, so I'm going to lock that reference, both of those. And then the order, I'm going to tell it 1 to say ascending. It doesn't really matter. You can do up or down. It's all the same. And then copy and paste them, and now I have them all ranked. But then I want to do one more modification. I'm going to do +1 over there. And the reason I want to do +1 is so now I have not only ranked, but I have them ranked 2 through 21, which matches the rows that the data is found in, and that's going to be important. So now when I resample, I'm going to use that indirect reference that we've used in the past, and I'm going to tell it, quotations, I'm going to tell it to look in the B column, so I'm going to pull from my second data set, and I want it to use this number. So I'm going to have it look in the column that is, or the cell that is the number associated with this randomly chosen rank of these random numbers. And I'm going to copy and paste that all the way down. And what that's going to do is it's going to perfectly shuffle the data set I have right here, because these ranks are random because they depend on these random numbers. So now I have a perfect reshuffle, and because they are shuffled totally at random, I know that there is no correlation between these numbers and these numbers because that random number generator has erased any possible correlation. So now I'm going to use Excel, and it actually can calculate the correlation coefficient for us, which is denoted by R. And I want to first find my experimental correlation, so I'm going to do the true data sets here to find my correlation coefficient. And then I'm going to do the same thing to find the correlation between my first data sets and my completely shuffled data set that I know has no correlation to the first one. And you can see that it's not a zero number. There is, just due to random chance, some correlation between the two numbers almost every time. It's there, that one's almost zero, but most of the time there is, due to chance, some correlation. That one's pretty high. So how tightly correlated do the two data sets have to be in order to be confident that it's not due only to chance? Well, we're going to do another what-if analysis. I'm going to skip this step in this video, but I'm going to create a table here the same way I've done in the past to do a great many trials. I'm going to do my bins and frequencies, and now I'm going to plot those frequencies to see what happens if I were to do this random shuffle a great many times. And you can see I have a nice, neat bell curve across my correlation coefficients, with it being centered around 0, because there isn't any correlation. The real answer is there is no correlation. And then as we go out to greater and greater correlation, either positive or negative, it is more and more unlikely. Why is this useful? Well, we can find the coefficient of determination, which is just the correlation coefficient squared. And R squared is useful because we can look at those frequencies and it's going to collapse, and because we're squaring it, it's also going to be only positive. So I'm going to look at a more condensed data set that is only positive here for my R squared numbers, And R squared is great for when we do our regression analysis. So if I look here, an R squared value of about 0.3 or greater appears to be significant at a 5% confidence level. So anything that is an R squared value of 0.3 or more is a significant correlation of some kind. And so that's useful if we have a data set that we want to know if there is a correlation or not. So I've gone ahead and plotted some absorbance values at some arbitrary concentrations. And I'm going to use a trend line to try to describe what I'm seeing happen in this data set. And this trend line, Excel is super helpful because they will give us both the equation and they will give us the R squared value for our trend line. That R squared value tells us how correlated are the numbers produced by this trend line to the actual numbers in our data set. And we can see we have an R squared value of 0.99. And if we look back over here, we see 0.99 just does not happen due only to chance. So we know that that is a very tightly correlated trend line. That's going to give us a really good prediction of various values that we put into that trend line. So from here, with a well-fit trend line, I can now solve, if I know an absorbance is Y values, so I can insert an absorbance number for Y and solve for X to find the concentration that produced that absorbance. Or I can work the other way around, and I can put in a concentration for the X value at both of these X's, and then solve for Y to know what absorbance I would predict to see at that particular concentration. But we know that those predictions are useful because we can evaluate the R squared number that's been given to us by Excel, and this distribution of R squareds tells us what's significant and what is not.